Assalamu alaikum everyone. I welcome you all in my channel and you are watching CSS by SS, and today we will be talking about error checking methods, that what type of we can use when we are transferring our data, right? So our objectives will be: how does errors occur, how can errors cause a problem, and how is data represented, and then we will be talking about methods of error detections. How do errors occur? So there are three ways errors can occur. The first one is interference, second one is problems during the packet switching, third is skewing of data. And while interference, there are further three ways: data can be lost, data can be gained, and data can be changed, right? How can errors cause problems? Some errors are small and trivial, such as single swapped letter in a larger text. Let's say your name is how, and somebody will say you wow, right? So just H is replaced with W. So this is also an error. Other is errors in data such as postage addresses, aerospace coordinators, or bank transfers can be difficult to rectify or be disastrous. Any job or task that relies on a computer to perform highly sensitive or secure processes must have methods of error checking and correction. How is data represented? So all the data in computer science is represented in binary as a 1 and 0. 1 represents high voltage and 0 represents low voltage. For example, the number 67 is represented as a 01, a 000011, right? And an error caused could cause one of the bits to flip one from 1 to 0, right? And if the six most significant bit is flipped, right? So then we can get 67 another number instead of 67. Okay, by flipping a single bit, the meaning of the binary string has been changed. If a book was transferring over a network, assuming many bits were flipped, it would likely be difficult to read the original text. So there are multiple methods we can use for identification or detecting the errors. First one is parity check, checksum, echo check, and automatic repeat request. Parity check. It is the most commonly used method for error detection. The parity checking protocol determines whether bits in a transmission have been corrupted. Every byte transmitted has one of its bits allocated as a parity bit. The sender and receiver must agree before transmitting transmission whether they are using odd parity or even parity. So there are two types of parity, even and odd. If if sender is using even parity, the receiver must know that we are using even parity. Same goes with the odd parity as well. The value of the parity bit is determined by counting the number of ones in the byte, including the parity bit. If the number of ones doesn't match the agreed parity, then it means then there is an error in the data. Parity check only check that error has been occurred, but that do not reveal where the errors has been occurred. So this is the big problem in the parity check, that it tells us that there is an error in the data, but it doesn't reveal that where is that error occurred. Even parity. If an even parity bit is used, then all bits in the byte, including the parity bit, must add up to an even number. So let's say there are 4 ones in the data. You see, we have this data and there are 4 ones and we're using even parity, right? So if there is, this means that parity bit must be 0, otherwise the whole byte, including the parity bit, would add up to 1, which is an odd number, right? So you have to count the number of ones in your data. It's 1, 2, 3, 4. It's already 4. It's even. So we are going to add 0 as a parity bit. In the odd parity bit, if an odd parity bit is used, then all bits in the byte, including the parity bit, must add up to an odd number. Let's say in this example we have 1, 2, 3, 4 ones in our data. So we will be adding 1 as a parity bit because we are using odd parity, and for odd we must have odd number of ones. We have already 4 ones, so when we will add 1, so it will become 5 ones, so it's an odd number. Okay, so this table shows a number of examples of a great parity between a sender and receiver and the parity bit used for each byte. So this is your data, and you have to tell me total number of ones and total number of parity bit, which parity bit you will use. In the odd, here in the first example we are using 1. See, we are using odd parity bit, and 1, 2, 3, 4 and 5 we have already 5 ones, so we will be using 0 as a parity bit, right? And in the second example we are using even parity, and we have just one number, so number of ones is 1, and we are using 1 as a parity bit, right? So in the same way you can solve all the problems. See, here you have to identify that do we have any error in the system or not. So in the first example they have used odd parity, and see, they have used odd parity. Parity bit is 1, and let's just count the number of ones. 1, 2, 3, 4, 5, and 6. 6. Total number of ones is 6. It means there is an error because we are using odd parity. Even parity. 1, 2. Total number of ones 2. It means there is no error. Point number 3. Even parity is using 1, 2, 3, 4, 5, 6, 7. 7 number of ones, but we are using even parity, so there is an error as well, right? So same ways you can do all the other things. Okay, so see, find out. Parity checks are quick and easy to implement, but fail to detect bit swaps that cause the parity to remain the same. So in the first example, see, we are using odd parity. Let's just count the number of ones. 1, 2, 3, 4, 5. And its number of ones is 5. It means there is no error. But on the receiver end, receiver received this number of bits, and you can see there are less number of ones. There are 3 number of ones, but it's odd, so we can't say that it's there is an error because we have already have this odd number, because we 2 bits or 4 bits has been swapped, right? So it's that's why parity bit is not easy to use, not easy to it will actually tell us, it will actually detect the errors, but it will not tell you that where exactly the error has been occurred. To overcome that problems, we develop parity bytes and parity blocks. Parity check do not pinpoint errors in data, only that an error has occurred. So parity block and parity byte can be used to check an error has occurred and where the error is located. A parity block consists of a block of data with the number of ones totalized horizontally and vertically. A parity byte is also sent with the data which contains the parity bits from the vertical parity calculations. See what happens in the parity block and parity byte. This is my parity bit and this is my parity byte. Okay, so this is my byte 1, byte 2, byte 3, byte 4, 5, 6, 7, 8, and this is my bit 1, 2, 3, 4, so on, right? So we are using odd parity 1, 2, 3, 4, 5. It's already odd, so we are using 0 as a parity bit. In the second byte, 1. 1 is already odd, so we are using 0. And in the third, 1, 2, 3, 4, 5. 5 bits. And then we have to make it's 1, 2, 3, 4, 5, and 6. So we have used this is not required actually, right? See, we have already used 5 parity bits, so 5 ones over here, and one more bit. We have to require to use 0 over here, but they have mentioned 1. So let's just see, just highlight this and we will be talking about in detail later. 1, 2, 3, and 4. This is right. 1, 2, 3, 4. This is also right. 1, 2, 3, 4, 5. This is also right. 1, 2, 3, 4, 5. This is also right. 1, 2, 3, and this is also right. Now let's just calculate from column wise, right? 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So see, it's also even. So let's just highlight this row as well, this column, because here we have even number of ones. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See? So here we have same one row and one column which is having some problem. But the place where our lines are actually intersecting, this bit is actually making some problems, right? So this is the advantage of adding parity byte and parity bit. So easily we can identify that where our error has been occurred. So this is the bit which has been changed while transferring from our data from one place to another. See? Okay, so the next method is checksums. So checksum determines if the data has been corrupted but do not reveal where. Same problem. Data is sent in blocks and an additional checksum value is added at the end of the block. Checksum are custom created user created algorithms that perform mathematical calculation on data. An example of a custom checksum algorithm in computer science is CRC. It's a hex number we will be generating to check the errors. What's the checksum process? Checksum process is very simple that when the data is about to transmit, the checksum value from the block of data is calculated. The value is calculated according to algorithm agreed by sender or receiver. The checksum has been added with the block of data. At the receiver end, the checksum recalculated using block of data. If the two checksum are same, then no transmission error has been occurred. Otherwise, request has been made to resend the block of data. Next, echo check. Echo check involves transmitting the received data back to the sender. The sender then checks the data to see if any error occur during transmission. This method is not reliable. As you can see, error would have occurred when the receiver transmit the data and when the receiver transmit the data. When receiver transmit the data, neither will know when the error occurred. If an error does occur, the sender will retransmit the data. Okay, so here we have an example for you. So they can ask this type of a question in your exams. 4 7 bits binary values are transmitted from one computer to another. These 4 7 bits binary has been given. 8-bit binary has been given, and it is transmitted from one computer to another. Parity bit is added to each binary value, creating each 8-bit binary value. So the original data value is 7 bits, right? But these 7 bits, this is my data, and the eighth value is basically my parity bit, right? So all the binary values are transmitted and received correctly. So they are saying that this value has been transmitted and received correctly. So what we have to do, identify whether each 8-bit binary value has been sent using odd or even parity by writing odd or even in the type of parity column. So it's very simple. We just have to find out the number of, count the number of ones, 1, 2, 3. So here we have 3 ones. So it means odd parity. 1, 2, 3. 1, 2, 3. This is also odd parity. 1, 2. So it's going to be even parity. 1, 2, 3, 4. 4. So this is also even parity. It contains 3. This is 2. And this is number of ones 4. Next, check digits. It's also the method to check the errors in our code in our data. It's the final digit included in code. It is calculated from all the other digits in the code. Check digits to determine if data has been corrupted but do not reveal where. Data is sent in blocks. An additional check digit value is added at the end of the block. Check digits are custom user created algorithms that perform mathematical calculation on data. An example of a check digit is the ISBN value on books and VIN. There are two methods used for check digits, ISBN 13 and modulo 11. We have already talked about this barcode. So in our input output devices, if you want to know more about barcodes, you can go and check out. So in the last value, in our barcodes, usually this last value is called check digit. ISBN 13. There are two methods to find out, uh, two steps basically. First, generation of check digit and then verification of digit. How we can generate check digit? To calculate an ISBN 13 check digit, the following algorithm is performed on any barcode value. Add all the odd digits together. First step is add all the odd digits together. Add all the even digits together and multiply it with 3. And the result from 1 and 2 divide by 10. Take the remainder. If it is 0, then use this value. Otherwise, subtract the remainder from 10 to find the check digit. For verification, you will again take 13 digits or any 13 digits of ISBN barcode number. You will add all the even digits together, including check digit as well. Add all the odd digits together, multiply with 3. Add the results from 1 and 2 and divide by 2. If the remainder is 0, then your answer is correct. Modulo 11. This method can be varying length of numbers which make it suitable for many applications such as product code VINs. It's also have two steps, generation of check digit and verification of digit. Generation of check digit, we can assume that 7 digits number. So we will give all the 7 digits number to weight starting from 0 and starting from the left side. 2, 3, 4, 5, and we will multiply weights with their numbers and then add all the numbers. We will got some total and then we will divide this total with 11 and we will got some remainder. Subtract remainder from 11 and that's are check digit. How to verify check digit? In Modulo 11, you will add check digit at the end of your code and you will weight that check digit to 1. Again, you will multiply all the check digits with its weighting values, then add them, and you will got some total, then divide them with 11, you will got some remainder, then subtract that remainder from 0, uh, divide. When you will divide some numbers, you will got some remainder. If the remainder is 0, then it means the number is correct, otherwise number is. Next process is automatic repeat request. So when the receiver receives transmitted data, it must check for the presence of any error. Errors can usually be detected but not always pinpointed. An automatic repeat request is a protocol that notifies the sender that an error has occurred and that the data received is incorrect. It works as follows. If an error is detected, the receiver sends a negative acknowledgement transmission to indicate the data is corrupted. If no error is detected, the receiver sends a positive acknowledgement transmission, meaning the data is correct. If the receiver doesn't send any acknowledgement transmission, then the sender waits for a certain time period, known as timeout, before automatically resending the data. This process is repeated until all data has been received and acknowledged. So this process is called automatic repeat request. So why network security for systems? There are many threats exist to systems in network security. For example, malware, viruses, spyware, hackers, denial of services attack, social engineering, SQL injection, and there are a lot of others as well. Some of them has we have already covered, and some of them we will be covering in our further slides. Hacker and eavesdroppers. Hackers are basically the persons who try to gain unlawful or unauthorized access to computers, networks, and data by writing programs. They look for weaknesses in the system and use them to gain access. Hackers have various motives, such as financial gain, a challenge, or a protest, etc. Hackers sometimes target data in order to steal and use it or block people from using the data by creating programs called ransomware. Hackers may also use packet sniffers to intercept and read data transmitted across the internet or a network. Hackers will often want to use people's information and therefore it is beneficial to encrypt your data. That's all for today. If you like my video, please subscribe my channel and share it with your friends. Thank you so much. Allah Hafiz.